Okay, so today I'd like to talk about something a little bit different. So I've been talking about higher categories and showing how a lot of math gets unified in them, and that could go on for a long time. And I'm going to go on and talk about combinatorics and category theory. But this lecture is about something connected to the braid group. So it's vaguely related to what I've been talking about. Namely, I showed this periodic table of n categories, and one of the most interesting early entries in that chart is the braided monoidal categories, which are categories where you have a way of switching objects, but there's a way of switching one in front of the other or behind the other. And in traditional mathematics, you don't have that distinction. If I have the map from the set x times y to the set y times x, you don't ask about whether you're switching the elements from x in front of the elements of y or behind. That doesn't make any sense. That's called a symmetric monoidal category, and those are the ones that you're used to. But braided monoidal categories burst into prominence in the 80s. And so that's underlying the math here, but you don't need to know about those categories at all to understand what I'm talking about. So this particular group called B3, the three-strand braid group, connects a whole bunch of fascinating mathematics in really exciting ways that I haven't gotten to the bottom of. And I just discovered right before I gave this talk that Conway wrote a whole paper about this that I hadn't known about. But so the theorem that starts it off, probably due to Artin. It's a special case of a theorem by Artin, and I'll just state it, and then I'll explain it. So B3 is some group, and the theorem says that you can describe it using generators and relations, where you have two generators, say A and B, and one relation, ABA equals BAB. Okay, so what is this group B3? So the three-strand braid group has elements that are, guess what? Braids with three strands. So a typical element of the three-strand braid group might look like this. So here you think of this as sitting inside a cube, for example, and you think of these strands as curves that are embedded in the cube, and their positions are nailed to the ceiling at certain standard locations and nailed to the floor at the same standard locations, but they're free to wiggle around without crossing each other inside. So the details of how I drew it don't much matter. So like it would be equal to this, to this braid where I had drawn the little wiggle in there. And then the way it becomes a group is that you multiply these braids by sticking one on top of the other. So if here's some braid, say X, and here's some braid Y, so we could put this braid Y down in this next cube here, and we compose them just by sticking them together and then reparametrizing this cuboid here so that it becomes the unit cube again. And so then we'd get the product braid X times Y. And you can check that braids have inverses. For example, this braid here would have an inverse, which consists of crossing the first two strands in the other way, because you can wiggle these strands around without crossing each other to straighten them out. And then you get the identity element. So the identity element of the group is this braid here. If you stick it on top of something, it doesn't change anything. So that's the idea of what the three-strand braid group is. So what are these generators? And so the A is just the braid where the first two strands switch places, and I'm going to switch them in this particular way where the right-hand one goes on top. So A inverse would be where the left one goes on top. And then B is similarly the braid where the second two strands get switched. And then this relation, ABA equals BAB, is a very famous thing in topology. It goes by the name of the third Reidemeister move. And so what it says, anyway, in terms of pictures, what it says is just this, that so AVA equals BAB. What it says is that if you switch the first two strands and then the second two strands and then the first, you get a braid like that. And that can be deformed, wiggled around, so that you get this braid where you switch the second two and then the first two and then the second two. So you have to stare at this. But only, yeah, is that right? Wow, it doesn't even look right to me. What? Yeah, it's right. It better be right. So yeah, you have to, it takes a while to stare at it to see why it's true. One way to think about why it's true is that this strand going from the far left to the far right is behind both of the other two in each picture. So it's not getting in the way. And then the other two, the second and the third strand, they are switching places with the third one going in front. And that's also happening here. So all that's happened is that this switch here has basically been moved up so that now it's over here. So they're equal in the braid group. So the hard part, of course, of the theorem is to check that this is the only relation you need, that all other relations that hold in B3 can be derived from this one. So I'm not going to attempt to prove that, but that's a famous theorem called Artin's theorem. And he did it not just for 3-strand braids, but a similar, more general theorem for any number of strands. So why am I so interested in the 3-strand braid group? Well, one reason why is that there's a very interesting relation between that group and some other famous groups. So there's a homomorphism, and it's onto, so there's a surjective homomorphism, or epimorphism, if you prefer Greek to Latin, or onto homomorphism, if you prefer English, but who likes that? So there's a surjective homomorphism from the 3-strand braid group to this other extremely famous group called SL2Z, or SL2Z. And this is the group of 2x2 matrices with integer, 2x2 matrices with integer coefficients. Matrices are linear transformations, but not all of them, just the ones that are special, namely the determinant is 1. So these are 2x2 integer matrices with determinant 1. And the way it works is that the braid A gets sent to this matrix here, and the braid B gets sent to this lower triangular matrix, very similar looking, but with a minus sign here. So what's going on is that both A and B are getting sent to certain matrices that clearly have determinant 1 and integer entries, but they're very nice matrices. They are shears. So as a linear transformation, this first matrix says change X, replace it with X plus Y. So you add Y to the X coordinate and leave the Y coordinate alone. So that's a shear in the sense that one coordinate is affecting the other, but not vice versa. And this other one here says, leave X alone, but then replace Y with Y minus X. So in the first one, you're adding Y to X, and the second one, you're subtracting X from Y. And so the interesting part, well, there are a couple of interesting parts. So first of all, well, okay, no, the most interesting part is that it really is a homomorphism, that you really can define a homomorphism this way. And to check that that's true, if you believe Artin's theorem, you just need to check that the relations get preserved. So you need to check that PA, PB, PA is PB, PA, PB. In other words, that these two matrices obey the same type of relation. And here's where I did that. check. So what I'm doing is I'm taking these shears and I'm applying them to a little square whose edges start out being the standard unit vectors in R2, the standard basis vectors in R2. And so here, what we're doing is PA. So we're adding the y coordinate to the x coordinate. So it tilts it over like this. And then we're subtracting the x coordinate from the y coordinate. So this is like 1 up. Sorry, here the x coordinate is 2. So we subtract 2 from this and we go down here, etc. And then now we do PA again. So now we're adding the x coordinate to the y coordinate, but the x coordinate in the square is negative. Like here it's -1. So we add -1 to the y, to the y coordinate is -1, and so we add that to the x coordinate, and it shears it back there. So what this has done is it's taken this square and it's actually rotated it 90 degrees clockwise. And then we could also do PB, PA, PB. So you have to stare at this. I see Tom staring at it with his eagle eyes. You can see him verifying it. He's my proof assistant. If he frowns, it means the proof it's wrong. If he smiles at the end, it means it's right. And so he's laughing. So I assume that means it's right. So yeah. So it works. So we're seeing that we really do have a homomorphism defined in this way. And then there's something else you have to check, of course, which is that it's surjective. So that's just a fact about matrices. You just need to check that every matrix in SL2Z can be built up of a product of these guys and their inverses. And I'm not going to check that. I mean, I'm not saying it's instantly obvious or anything, but that can be checked. So that's nice. So SL2Z shows up all over the place, for example, in number theory, the study of elliptic curves, the study of continued fractions. And so this is starting to sound nice. One interesting thing, though, is this, so we saw that PABA is the same as PBAB, and both of these are a quarter of a full turn rotation. I mean, it's a quarter turn clockwise, for what that's worth. So then that means that if you square it, so I could square either one of these, but it's even more fun to do this one times this one, since they're equal. That's the same as squaring it. So that's P of ABA, BAB. So that's a half turn. And so it has to be the matrix -1, -1, 0, 0. And this is also, of course, the same thing as P of AB cubed. The reason why this is interesting, for one reason, is that this matrix -1 is in the center of SL2Z. It commutes with everything. And in fact, the center of SL2Z is just the identity and negative the identity. Those are the only matrices in there. So this thing plays a special role. So it generates the center of SL2Z. But then another instant consequence of all that is that so we took AB cubed and we applied P to it and we got minus the identity, but that means if we take AB to the 6th, we get the identity. So P of AB to the 6th is also very interesting thing. It's just the identity. So that means that AB to the sixth is in the kernel of this homomorphism here. And then a much less trivial fact is that it generates the kernel of that homomorphism, so that everything in the kernel is generated by this one marvelous element here. I don't know who first proved that, but I once saw it in a paper by Tuba and Wenzel. So, I mean, I don't know if they deserve credit for it, if they were just observing it. That could be a very well, I wouldn't be surprised if that's a much older result. So AB to the sixth generates kernel of P. So we have this nice relationship between the three-strand braid group and this famous group SL2Z. So we get the exact sequence where you have the braid group mapping onto SL2Z. I guess I'll write 1 here, since I'm thinking of these groups sort of multiplicatively. And this is P. And then the kernel is a copy of Z, the integers, generated by AB to the sixth. So AB to the sixth, sorry, so the number 1 in here is getting mapped to AB. Well, over here, it's written additively. Right, this, so I can really confuse you. Yeah, let's do it. Let's do it. Let's do it. Let's confuse the hell out of people. So, but I mean, the group operation here is addition, and here it's matrix multiplication. So I don't know what the correct notation is for such situations. But anyway, the main thing is that this guy here generates the kernel. The other interesting thing about all this is that these, yeah, sure. Sure. Uh-huh. It's a group, the three-strand braid group, yeah. Yes. Yeah, in 4 dimensions, there'd be no difference between crossing in front and in back. In 2 dimensions, there'd be no room for them to cross each other. So 3D is where braids live. Uh-huh. Yeah. Yeah, so in terms of that periodic table stuff I'd been talking about earlier, there's like one slot in the periodic table, which is for studying one-dimensional things sitting inside 3-dimensional space. And that's where that's the slot where you get interested in things like knots and braids.
What about 2D things in 4D space?
Well, you want me to give another talk? So the other interesting thing about all this is that these special elements, AB cubed, which generates the center of B3, and AB6, which generates the kernel here, they're very appealing characters in the following sense. So AB cubed, you can think of it as a ABA, ABA again, because ABA is equal to BAB. So here I drew here I drew BAB, BAB, but BAB is ABA. So it looks like this. And you can see what's going on is that things are getting turned around. This is a full, now you look very unhappy. No, remember, this is equal to lots of other things. This is equal to BA cubed, and it's equal to ABA. And
I guess I'm seeing the fact that you've got 4 crossings in your diagram.
Oh, did I screw up? 1, 2, oh, did I just, I didn't do enough of them. What did I do? This is let me just draw it so that it actually looks like, Yeah, that was AB squared. And let me draw it in such a way such that the A comes before the B. We're doing multiplication from left to right here and from top to down here. So why don't I draw it in a way that I'm not like exploiting any sneaky stuff. So there's AB drawn nicely. And you're right, I screwed up. I will do it again. And then I need to do it a third time. Thanks. Yeah, that's really important. Sorry, that is such an ugly picture. So what has gone on here? What has happened is that we've given, if you think of this as like a big blob of stuff, like a, grab someone's hair and they just happen to have just 3 hairs, and we twisted it 360 degrees. It's a full turn. So the hair on the left got rotated all the way around and comes back to the left. The one in the middle comes all the way back to the middle. The one in the back comes all the way back to the one in the back winds up in the back. So this is what I'd call like a full twist. It's a 360-degree full twist of these 3 guys. And that's part of how you prove it's in the center. You could prove that for any other braid, a full twist will commute with it. Well, you have to draw some pictures to convince yourself of that. And so then what this AB to the 6th thing is very interesting. So this is a double twist. That is, it's 2 full twists, or a 720-degree twist of your braids. And so what we're saying is something interesting. We're saying that a double twist gets mapped to the identity in SL2Z. Remember, it was getting mapped to a full rotation of 360 degrees in the plane here. So something interesting is happening. You have to turn the braid around 2 times to get your matrix to be a 360-degree rotation, i.e. the identity. So P maps the double twist, 2 full twists, to a 360-degree rotation, which is just a fancy way of saying the identity, of course. Okay, now physicists out there, what does that make you think about? Spinners, spin 1/2 particles. So you know, or you've been told, that if you turn an electron around once, its state has actually changed. It's gotten multiplied by -1. But if you turn it around twice, it gets back to where it was. And that's exactly what we're seeing here, that this guy, the full twist, is getting mapped to -1 in SL2Z, but the double twist gets mapped to the identity. So something connected to the physics of spin 1/2 particles is emerging out of this braid group. Yes?
If we hold the top pieces and bottom pieces in place and like nail them there, but allow the braid to loop round the top as a whole,
then you can undo it. You can undo this one. You can completely undo this if you allow an illegal move where you move the braid up around outside the box. I could take off my belt and demonstrate that, but I might get a lawsuit or something for doing that. So I won't. That's a famous thing called the Dirac belt trick, back when math professors were allowed to remove their belt in class. And so, but I will not attempt that. So this is connected to spin 1/2 particles. And I don't want to get into that too much, but I can't, but it's important to bring in a little bit of what's going on here. So it's related to, so there's SO3, the group of rotations in ordinary three-dimensional space. And you might think that that's what you'd use to describe turning something around. But in quantum mechanics, it turns out you need to use a different group called SU2, the group of 2x2 unitary matrices that are special, that have determinant 1. And there's a 2-to-1 and onto homomorphism from one to the other. So So you only get back to the identity. So if you trace out a path here that goes all the way around this group and back to the identity, it actually corresponds to rotating around twice here. And that's sort of the math behind the spin 1/2 particles. So there's a homomorphism like that. Now, it turns out that that's just sort of the three-dimensional part of the story. There's also this thing called the Lorentz group, which is the group of transformations of four-dimensional space-time with 3 space and 1 time coordinate that preserve the so-called Minkowski metric on space-time. That group has 2 connected components, but if we take the identity component, the connected component of the identity, we get this nice group, and it's double covered by something very nice too. It's double covered by SL2C, the group of all 2x2 complex matrices with determinant 1. And this group is sitting inside here, and this group is sitting inside here as the ones that don't mess around with the 4th axis, the time axis. And there's a 2-to-1 homomorphism here, making this diagram commute. So this is like the space version of the story of spin 1/2 particles, and this is the space-time version. But once you get into thinking about SL2C, then you should start saying, hey, well, how is that related to what he'd been talking about before about SL2Z? Well, of course, SL2C contains SL2Z. But in fact, there's something very nice in between. There's SL2R, the group of 2x2 real matrices with determinant 1. So that's a subgroup of this. And it turns out that that's a double cover of something too. It's very nice. That's the double cover of the Lorentz group of 3-dimensional space-time. So now this is where you have 2 spatial coordinates and 1 time coordinate. And that's a subgroup of this. So like this would be like you have like X, Y, and T axes being acted on. And this would be like X, Y, Z, and T axes. So if we were 1 dimension down from our 3-dimensional space, our Lorentz group would be SL2R, or it would be this, and it would be double covered by SL2R. So that's very nice. But then what we're doing is something even weirder, which is we're saying, let's think about a discrete version of the whole story, where instead of using the real numbers, you just use integers. So that's a subgroup of SL2R. And that also double covers some group that's akin to these. It doesn't have any great name. Well, it does have a great name. It has a great name, but it's a different sort of name. They call it PSL2Z, the projective special linear group. But all it is it's just SL2Z modulo plus or minus, modulo the subgroup consisting of plus or minus the identity. So we see that this full twist here was getting mapped by P to minus the identity. And the double twist is getting mapped to the identity. So SL2Z double covers this group that's of some relevance to what we're talking about. And that's a subgroup of that. So all of this is meant to indicate that there's like a lot of nice patterns going on here. But what I really want to do is bring the 3-strand braid group into the act. What we saw is that the 3-strand braid group maps onto SL2Z. So let's get that into the story here. So what we had already was that the 3-strand braid group maps onto SL2Z by this map we've been calling P. So that's surjective. And then it has this kernel, which is a copy of Z. Sorry, having started this insanity, I'll continue it. We're calling it 0 over on that end. And then what I'm saying now is that all this stuff is like a discrete version, an integer-based version of something that you could study using number systems that are bigger than the integers. I could bring in both of these, but let me just bring in the real case. So SL2Z is sitting inside SL2R. Let's just bring in that one there. And then it turns out, what is the analogous thing to B3? Well, it turns out there's a group that wants to fit in this slot. And what it is it's the universal cover of SL2R. The universal cover of SL2R maps onto SL2R. That's how universal covering groups work. This group SL2R actually has its fundamental group is the integers. So its universal cover is not just a double cover, it's an infinitely many sheeted cover. So like over here, we had that like pi one of this guy was just Z mod 2. So the universal cover was just a double cover, and that's it. Over here, that was also true. But when you get over to here, because you're now, well, it has to do with a different dimension of space. When space is just two-dimensional, turning things around once, twice, 3 times, 4 times, they're all really different things to do. They are not homotopic paths in the rotation group or even in this larger Lorentz group. Whereas when you're in 3-dimensional space, turning around things twice is homotopic to not turning them around at all. So this is an infinitely many sheeted cover of this. So the kernel is Z. And in fact, there's a commutative diagram that works like this, where this is a inclusion. And this is just the identity here. So what I'm saying is that the Lorentz group in 3 dimensions has a double cover, which is SL2R, but the double cover is not the universal cover. You can keep on going, and the universal cover is an infinitely sheeted cover. So I'll just stick that in here. And so B3 is like a discrete subgroup of that. It is a discrete subgroup of that. I hate it when someone says something is like something when it actually is that, and I just did that. So I'll punish myself tonight. I'm thinking of like self-flagellating monks in their cell. So that's what I should do for saying like when I don't mean like. So, okay. So this is all very cool. And then there's a theorem which should follow from this using just a little bit of topology, but I've been feeling a little stupid and haven't been able to like come up with a slick proof of it just from this. But I'm sure that as soon as I say this, someone will, please don't interrupt my talk, but I do want to hear from you afterwards if you know how to prove this. So there's one beautiful fact that if you take SL2R mod SL2Z, that quotient, that's a quotient space. This is a topological group, and this is a topological subgroup. So this gets a topology. So you can talk about its fundamental group, and that turns out to be this 3-strand braid group. Now you might think, oh, well, that just should be immediate from this. And it probably is like almost immediate from this. I do know about the long exact homotopy, the long exact sequence of homotopy groups of a fibration. And there's a way to see that something is B3 using that, but that something doesn't instantly turn out to be this. So there's just probably like 2 more minutes of work by a skilled topologist beyond what I have done to derive this fact. But I will, yeah? Okay, sorry, yeah. I was hoping you just like tell me the 1-sentence proof, but it's okay. Don't tell me. I don't really actually want anyone to tell me the 1-sentence proof now. I do want to know it. But what I'll do instead is I'll give you a long and complicated proof that we'll use the rest of the talk. But this long and complicated proof is beautiful in its own way because it explains why you care about this space. Now, if you're a number theorist or something, you already know why you care about this proof, why you care about this space, but I will sort of introduce a bit of that. So first of all, this space SL2R mod SL2Z, it's included in a bigger space, which is GL2R mod. Actually, it's mapped to the space GL2R mod GL2Z. And it actually is an inclusion. And so the idea here is that this is all invertible 2x2 matrices with real entries or integer entries, whereas this, here we just have ones with determinant 1. They're just two choices of what the determinant could be for these guys. The determinant could be 1 or -1, but for this, it could be any non-zero real number. So this space is one dimension bigger than this because you could take anything in SL2R and multiply it by any positive real number, and you get a guy in GL2R or any negative real number. But for any positive real number, that's good enough to see that what's going on is that we're making this space bigger than this just by basically, I guess we're basically just taking its product with the positive real numbers. So this map here is a homotopy equivalence. We're adding on an extra dimension, but this extra dimension, namely the possible values of the determinant of this, are just going to be taking values in a line. So it doesn't change anything like the fundamental group. It's a homotopy equivalence. So we can just check that the fundamental group of this is the 3-strand braid group. And this group is very nice. So this, not group, it's a space. This space is very nice. This is the space of lattices in the plane. And I'm going to switch between thinking of the plane as R2, which is how we should start out thinking of it as, and later on in a minute, I'll start thinking of it as a complex plane. But the idea is that I can get a lattice in the plane from an element of GL2R. What I do is I just take the standard basis vectors in R2, and I apply any element of GL2R to them, and I get two new vectors, and then their sums and differences, their integer linear combinations give me a lattice. So I can get any lattice that way. A lattice is just a discrete abelian group sitting in R2. I guess it's also a free group of rank 2. So we can get any lattice that way, but it's possible to change the transformation G and still get the same lattice, because I could just add any integer combination of E2 to E1 or vice versa, and I would get the same lattice. So there's a subgroup, namely GL2Z, that is acting in such a way that for any element of GL2Z, we get the same lattice as if we'd used the identity. So this is the space of lattices.
What if your element GL2Z was 2i?
Sorry, what's 2i? That's not in GL2Z. That's not invertible in an integer. Yeah, so it has to be invertible and have its inverse be an integer matrix. So the only possible determinants of these guys are 1 and -1. Yeah. Thanks, though, for asking that. We got to get this. Get some sense of this. And I'm sort of whizzing along here. So let's call that guy X. So that's a very nice space. It's the space of lattices in the plane. And now it turns out that there are two very famous functions on this space of lattices that people use to classify lattices. And they have the scary name of modular forms. Scary or lovable, depending on where you are in life. So there are functions which I'll call, which people call G2 and G3. they're complex valued functions, they're continuous. And they're just functions of a lattice, and they work like this. I'm going to stick some weird numbers in here, which don't really matter too much, but it'll help me a little bit. So what we do is we sum over all points in the lattice, but we're going to think now of that lattice as sitting inside the complex plane. So we'll think of the lattice points as complex numbers. And what we'll do is we'll sum 1 over z to the 4th. So that's just some weird way to get a number from a lattice. It would be very bad if z was 0, though. So we sum over non-zero lattice points. And the 20 here is just to make some other formula look simpler. And then G3 is a similar thing, but instead of the 4th power, we use the 6th power. And people like thinking about these things for all sorts of powers, as long as the power is big enough to make the sum converge. So these are called, like, I guess they're called Eisenstein series or something. Maybe Eisenstein functions or something like that. And there's so I could like look at G4 and so on. But the thing is that these are enough. These two turn out to be enough to completely classify lattices. So there's this theorem. If you give me two numbers, complex numbers, and if they obey some little restriction that a cubed is not equal to b squared, maybe I'll say it like this: a cubed minus b squared is not equal to 0, there exists a unique lattice where these functions take those values. So this is a theorem that's sort of like a basic, crucial, I was not saying it's as basic, but not trivial, theorem about the theory of modular forms. So this is modular form theory. And what's this weirdo restriction, a cubed not equal to b squared? Well, it turns out that there are lots of lattices, but one thing that lattices can do is they can get closer and closer to, they can get sort of flatter and flatter. So you can imagine a one parameter family of lattices that sort of flatten out like that. And as they flatten out, they approach something that's just a one-dimensional thing that's not a lattice. And as they flatten out, this quantity, a cubed minus b squared, approaches 0. So this just rules out, this just kills off these subgroups of the complex plane that aren't abelian groups, that aren't lattices, and this thing here is famous. It's called the discriminant. It's called, I guess, the modular discriminant. I mean, a discriminant is just something that shouldn't be 0 if you want things to be nice. And this is the one that shows up here. So this is a bunch of non-trivial stuff, but what we can use it for is to understand the topology of the space of lattices. Because what we've seen, or what I've claimed, is that a lattice is just the same as a pair of complex numbers with this condition here. So this space of lattices act to the subset of C2, the subset of pairs of complex numbers, where this condition holds. And so we can use that to understand its fundamental group. And now this space is sort of big, but it's big because we can multiply A and B by suitable constants and have this continue to be true. And so this turns out to be diffeomorphic to R plus the positive real numbers times the smaller space where we demand that the pair of complex numbers lies in the unit sphere in C2. Right? Because you can just rescale A and B suitably to get this to equal 1. And the rescaling factor would be some positive real number. So this is very nice because if we drop this condition here, we're just taking the unit sphere in C2. C2 is a 4-dimensional real vector space. So that's the 3-sphere. So this is isomorphic to the 3-sphere. Sorry, well, this one. That is isomorphic to the 3-sphere minus this set where a cubed minus b squared is equal to 0. And that set in the 3-sphere, so here I'm thinking of the 3-sphere, right, as in C2. That set there, that turns out to be a famous thing. It's the trefoil knot. It's a knot. You can think of knots not only in R3, but in S3, and they work almost the same way. Because you're just adding on a point in infinity to get the 3-sphere, and when you're playing around with knots, you can just always avoid that point at infinity. And sorry, I'm writing it like this, which is bad. This is, well, I'm writing it in a way that's bad because I sort of, over here, I should remind you that we're demanding that it's in the 3-sphere. So if you think about this for a while, you can figure out that it is the trefoil knot. The key picture is to imagine a torus, and imagine a curve on a torus that wraps around the torus and goes 3 times around in one direction while it's going around 2 times the other direction. That's what this condition is implying. It's saying that if you change the phase of B, you have to change the phase of A, and one of them has to go, I guess this one has to go around, B has to go around 3 times for each 2 times A goes around. So you get this, if you think about it for a while, you get this kind of curve where this thing goes around. Oh no, I'm probably gonna draw it terribly. Let me just draw it. Let me not try to draw it on the torus, because that will defeat my current drawing ability when I'm whizzing along here. So you get this kind of thing. So this is what T looks like. And then, so the trefoil knot is somehow connected to modular forms. And now that's the way that we see that the fundamental group of this space here is the 3-strand braid group. Notice that multiplying by a contractible thing, a contractible space, doesn't change the fundamental group. So we just need to show that the fundamental group of S3 minus T is the 3-strand braid group. So why is that? Well, it turns out that there's a way to calculate the fundamental group of a knot complement, the complement of a knot in the 3-sphere. And the way it works is that for each, you just draw a picture of your knot, and you should probably orient it. And for each little part that you can draw without going under another section of your drawing, you get a generator. And for each crossing, you get a relation. So this is called Vertinger's theorem. It's a general way to calculate fundamental groups of knot complements. And if you apply it in this particular case, here's what it says. It says you get the group generated by three guys, A, B, and C, and the relations come from the crossings. And they say, in this case, they say that if you conjugate B by A, you get C, because when you cross over A by B, out pops C. That's mystically the reason for why it shows up. And cyclic permutations thereof. So these three different crossings give you these three different relations. And then you can check, do I have time? I won't have time. You can check that this group is isomorphic to the three-strand braid group. There's an isomorphism from the three-strand braid group to here, and the isomorphism does the obvious nice thing. It sends A to the thing that I'm calling A, and it sends B to the thing I'm calling B. And you might say, what about C? Why isn't that getting it? Well, C is not independent from A and B. So if I'd had a bit more time, I would have just derived these relations from the ABA equals BAB, but I leave that to you. It's easy enough to do. So something magical has occurred here. I hope you agree. And I would like to understand it better, but we're seeing that modular forms are related to spinners, which are related to these funny spinners with just integer entries, which are related to the three-strand braid group and the trefoil knot. And people know a lot about this, but I think it's still mysterious. So thanks. Yep.
It looks like it's somehow related to Weierstrass elliptic function.
Yeah, the Weierstrass elliptic function should also be in this picture. Sorry, I can't quite put my finger on it, but part of the point is that, what is the point? Yeah, these two guys are telling you what your lattice is. But then once you have your lattice, you can define the Weierstrass elliptic function on C mod that lattice. And it turns out that there's a very nice algebra which consists of G2, G3, and the Weierstrass elliptic function. Yeah, and if I remembered it, I would tell it to you, but they do fit into a package.
For braids, you can
four strands. Four braids.
You can find the inverse just by sticking the mirror to the top or to the bottom.
Yeah.
And then the way to continuously deform that thing into the straightforward or three parallel lines identity is just to slowly move the mirror upwards.
Yes, that's the way that you check that any braid has an inverse. Yep. Did you have a question? Yeah.
So can you see that the braid group gives a 2-to-1 mapping to SL2?
No, B3 gives a infinite to 1 mapping. The kernel of that map from B3 to SL2Z was infinite. It was everything generated by the AB to the 6th. So you see, yeah, so it's related to the fact that the universal cover of SL2R has an infinite to 1 map to SL2R, which then has a double cover to this PSL2R, which is the Lorentz group. So you're used to mainly doing physics in higher dimensions where Lorentz groups just have an interesting double cover. But when space is just two-dimensional, then you get a very fun new thing going on. The Lorentz group and also the rotation group has an infinite many sheeted universal cover. And that's what they say gives rise to what are called anyons in two-dimensional space, as opposed to just bosons and fermions, so these other particles that you might need to rotate lots of times before they get back to where they started. And so the map from B3 to SL2Z is modding out by that infinitely many sheeted kind of thing. It's modding out by the powers of the double turn. Yeah. Yes? The what? Uh-huh.
The kernel that integral was so there's a sort of version of this in that section.
Huh.
It's quite very gallant.
Yeah, that must be connected to the southern modular form stuff.
Yeah, but it's sort of
yeah, so when I write up the notes to this talk, I will need to learn many more things to make it to fit the whole picture together. This is just like a piece of what's going on, but it's already, I think, sort of neat how a lot of different kinds of math are getting tied together. So.
Another thing that's useful to know is that PSL2B is the free product of the Z1 and the Z1-3.
Right.
SL2 is the amalgamated product of the 4 and the 6.
Uh-huh.
And B3 is the amalgamated product of two Z's over another Z where the maps are multiplied by 2 and multiplied by 3. So that gives you a really symmetric.
Yeah, I'll have to think about that. I know that some of that stuff that you just mentioned has to do with the fact that there are two specially symmetrical lattices, the square lattice, which has 4-fold symmetry, and the hexagonal lattice, which has 6-fold symmetry. And that's somehow part of this story, yes.
I think we should stop recording now because the mic won't be picking up the questions from the audience. So let's
okay.
Stop the recording now.
Thanks.